What we found last day was that magnetism was just flat out goofy. With the electric field and the electric force, all we had to keep straight was whether the electric force was in the same direction or the opposite direction. If we had an electric field that was towards the open door, well, that electric field was the force if my test charge was a +1 coulomb. And that meant that any positive charge would have a force, an electric force, in the same direction. But if I had a negative test charge, that negative test charge was going to be pushed with an electric force in the opposite direction. And that was challenging enough. Oh, is it the same or is it the opposite? But here what we find is that it's not the same direction, not the opposite direction, it's 90 degrees. Okay, we found that if we had this beam coming towards you, a beam of electrons, and we brought in this bar magnet, that the North Pole coming out of the bar magnet didn't push the beam to the right, didn't pull the beam to the left, but pushed the beam down. Okay, and I hope everyone has seen that by now. Okay, now, what we found last day, quick review, is in order for this magnetic force to act on a charged particle, that particle has to be moving. If it's just sitting on the table, you're not going to make a magnetic force act on it. Not only does it have to be moving, it has to be moving at least in part across the field lines. If these particles are moving along the field line, they don't feel any force. Or if they're moving opposite the field line, they don't feel any force. It's when they try to cut across the field that they feel the force. Now, here's the thing. The direction of that force is going to be perpendicular to two directions: the velocity vector and the magnetic field vector. What that means is that if I can draw those two vectors on one whiteboard, if that's my velocity vector and that's my magnetic field vector, if I can draw them on the same whiteboard, they define a plane. And the only two directions that are possible for the magnetic force are going to be out of the board or into the board. Now, in order to figure out which one it is, we use what's called the right-hand rule. And if you've been to tutorial, and I guess you all have, you know that there are 3 right-hand rules in this class. Only the first right-hand rule gives you the direction of the magnetic force. The other 2 right-hand rules are just memory devices to help you visualize the magnetic field. But the force is given by right-hand rule number 1. Because there has to be motion, that's principle, that's key. Because there has to be motion, you reach in the direction of the motion. The most important step is turning your wrist so that you can wave in the direction of the B field. Now I could wave in the direction of the B field like that, and at some point you'd hear a snap where my wrist cracks. Don't hurt yourself, okay? Turn your wrist and wave in the direction of the B field. Your thumb is in the direction that a magnetic force would act on a positive charge. So this would be the force on a positive test charge. This would be the direction of the force on a negative test charge. Now, folks, on the exam, I often see people that are solving problems during that exam and doing this
and hurting themselves.
People, it's your exam. It belongs to you. You can do whatever you want to it. Turn it around so that you can reach away from your body and turn your wrist and swing your hand so you don't hurt yourself, okay? Just always turn your test so that you're reaching away from your body, okay?